So we're going to look at some examples of finding the length of an arc. And we're going to look at examples where not the original function, but the final integral looks like this, which is a linear square root, or it looks like this, which is a perfect square. The perfect square is going to be the hardest one for you to handle because algebraically, the things you get do not look like perfect squares. And the reason for that is that the perfect squares that you're used to are quite nice. That's a perfect square. What do I mean by that? Well, if you factor it, both terms are the same, in which case you can write it down as a perfect square. Now, as long as the quadratic looks like that, everybody's kind of happy. Yeah, I can see that as a perfect square. But that's a perfect square. So let's just get some practice at making perfect squares. That is a perfect square. What is it? Any volunteers?
X squared plus 3 squared.
X squared plus 3 all squared. Yes. You see it now? This is weirder. That is a perfect square. Okay, now it's a perfect square. Now there's a trick to the ugly ones, and this is the ugly ones, right? You could try and figure out all the usual algebraic techniques, but the terms are just so messy that it'd be very hard for you to do it. So what you're going to do when you do one of these questions, these arc length questions, and you end up with inside the big square root, because they'll all be inside the square root, a guy that looks like this. You know that if there are 3 terms, it is going to be a perfect square, because it has to be or you can't do the question. The only exception to that would be when they ask you to give the answer to 10 decimal places or 2 decimal places, in which case don't you just plug into your calculator and don't worry about how it looks, right? So if they don't give you that get out, right, give me the answer to 2 decimal places, get out. This is a perfect square. And here's the trick. Put them in order. By that I mean highest power to lowest. Take each term on the first one, right? I'll call that the first term. And I'll call this guy the last term, number 3. Take number 1. Take each piece of it and take its square root. So that's a half x to the 4. Forget about the middle one. It'll sort itself out. Go to the end one, number 3. Each one of those 2 guys, take its square root. That's the perfect square of that. And you can check it by, old-fashioned foiling. But you can trust me, that is the end of this. That's that question done. Okay, let's try another one. Suppose I said to you, that guy. A lot of them are going to look like this, a positive and a negative power, right? So it's just the way they are. Any volunteers for what the perfect square would look like? Who's going to go first?
Is it going to be x to the 3 plus x to the negative 3?
Yep. Now, when you take the square root of a power, don't you just half its power? So an x6 becomes x cubed. And an x to the negative 3 becomes an x. So an x to the 8 would become an x to the 4, right? You could even get, God forbid it happened, but you could even get an x to the half. Wouldn't that become x to the quarter? Right? Half the power, right? So are we comfortable with how to deal with some weird perfect squares? How do we know they're perfect squares? They're going to be 3 terms inside your square root. You see 3 terms is a perfect square. Nothing else. Don't even look for anything else. Don't look for x subs. Don't look for u subs. Probably shouldn't even go look at the table of values. I don't think you'll find it there. Right? It's a perfect square. So now we need to get a question that does a perfect square. So let me go and hunting for one. This is a version of question 5. And it's y equals x cubed over 3 plus 1 over 4x. We got that guy. Might as well put the formula for arc length over here while I'm doing my thing. Okay. If you want to take this guy here, right, you have to differentiate him. I would probably rewrite this guy as a third, and I'd rewrite this guy as 1/4 to -1. This one especially, because if you're going to differentiate, aren't we going to use the power rule? And so we need powers, right? We don't want fractions. So its derivative, let's use that notation, multiply by the power, reduce the power by 1. Its derivative, multiply by the power, reduce the power by 1. Are you comfortable with the derivative being these 2 terms? Great. Okay. We're going to do 1 plus the derivative squared next. So derivative squared is x squared take away 1/4 x to -2 being squared. That's x squared take away 1/4 x to -2 times another x squared take away 1/4 to -2. And I'm taking this really slowly. You may not need every line, but I'm putting every line I can think of in. The reason I've written the square like this is so I can do FOIL. And you might think FOIL's easy. Well, most of the time it is, but not this time. And the reason it's not easy is there's a lot of negative powers floating about and some weird combinations as well. So let's start off with the F. Well, if you take x squared and you multiply it by another x squared, you get x to the 4. Nothing really strange about that. Here's our first strange one. What do you get if you multiply x squared with -1/4 x to the -2? Because something weird comes out of that combination.
Is it just 1/4?
With the negative in front of it. You all happy with that? Right, let's go inside. So that's the O, let's do the inside. Equally weird, just the order's slightly different. Do you see that that combination also gives you -1/4? Right, how does that happen? Well, isn't x to the -2 times x to the +2 x to the 0, which is just 1, so you end up with a number, in this case, -1/4. Are we all happy with the weird FOIL, for want of a better word, right? Now, what's the last going to look like? Well, a lot of people make a mistake on that one. They get everywhere, and then they kind of screw up on the last one. -1/4 x to the power of -2 times itself again. Right, as a number, won't you get the fraction part? Won't it be 1/16? What does x to the -2 times another x to the -2 give us?
X to the -4.
Correct. Now, if you tidy up, and there's not an awful lot of tidying up, but I'm doing it slowly. So far, so good. Now, I repeat myself, you probably won't do all of these lines, especially by the time you've done the 6th one. You'll start skipping lines because you'll do 2 things in your head at once. What I need to do now is add 1 to the derivative squared. So 1 plus, oops, that's a negative. And that gets me x to the 4 plus 1/2 plus 1/16 x to the negative 4. Do you recognise these 3 guys are going to be the guys that end up inside the square root? Do you also recognise there's 3 of them? And what did I say? If the square root had 3 things in it, I said it must be a perfect square, or else you ain't going to go anywhere. So here is our first weird perfect square. The way I've done my working is I've made sure that they're in order. That's important. Using this guy here, x to the 4, what should go here?
X squared.
Correct. Now this one, I don't care how weird it looks, just follow the rules and you'll be safe. It's plus 1/16 x to the negative 2. So what should go in the second term?
One-eighth x to the negative.
Not
second.
8th. Change the
Oh.
8th and 1. Yeah. X to the. And what power of x, Matthew?
Oh, -2.
Correct. Now it's almost like magic, isn't it? That this weird thing up here, right, eventually became a perfect square. So we can now get the arc length. It's going to be the integral from x equals 1 to 3, the square root of 1 plus the derivative squared. It's going to be the integral from 1 to 3, the square root of x squared plus 1/4 x to the negative 2 dx. And this is what makes perfect squares so nice. Isn't the square root of a perfect square cancel each other out? So you are now left with the integral from 1 to 3 of x squared 1/4 x to the negative 2. You've actually got an integral that you can do. Do you recognize this integral is just going to be the power rule? Right, nothing too weird. So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. I would change the second one from a negative power into a fraction so that style points first, and so it's easier to get an exact value secondly. Right, you plug in 3 here, what do you get? 1/3 3 cubed, take away 1/4 times 3, minus 1/3, take away 1/4. That's 9, take away 1/12, take away 1/3, add 1/4. I'm going to get a calculator to do this now. So I've got 9, subtract 1/12, subtract 1/3, add 1/4, and then just go math number 1. And the answer is 56/3. You notice that's a lot of work. Any question, Harrison?
I'm
No?
sorry, it's 53.6.
Yeah.
Good grief. Don't even that. I can't blame my scanning for that. I'm just careless. I'll start again. Oh, I know what I did. I transposed the digits. That's what I did. Can you see the amount of work that is involved in just one arc length that involves a perfect square, right? But at least you've got this one with every line I could possibly think of in it as your template, right? So if you look at another one, you can just say, okay, what's the steps? Because the steps don't really change much, right? Once you've done one of these, the next one's pretty much the same process, right? Pretty much the same process. I'm about to move this guy out the road. We good? Right. Let's find another perfect square. There's always ones floating around somewhere. And this one is like question 8. Y equals this fella, take away this fella. Oh, I just remembered something I hadn't done. Do you know that, actually, forget it. In this question, what I'm not going to do is I'm not going to evaluate it from 1 to 4, right? I'll do a ... before we get there. In fact, I might even do a ... about 3/4 of the way through this time because they are so long. Right, and I want to use every notation I can think of. So I called that y dot last time. Let's call it dy by dx this time. Maybe next time I'll call it f dash x, right? Just so you don't get caught up on one name only. Right, derivative, multiply by the power, reduce the power by 1. Okay, what's the derivative of a half log x? Derivative of a...
one.
Is it 1 over 2x?
Agreed? Yeah. Are we cool with that? Now I'm going to call that 1/2 x, take away 1/2 x to -1. Now I'm going to square it and add 1. So that's going to be 1 plus 1/2 x, take away 1/2 x to -1 times itself. Are you happy with me skipping the line there and writing the square as its FOIL? And also sticking a 1 at the front. Right, here it goes. The first two is a 1/2 x times another 1/2 x, gets you 1/4 x squared. Okay, here's the weird one. 1/2 x multiplied by -1/2 x to the -1. What's that guy and that guy going to give you when you put them together?
-1 over 4x to the -1.
Nope, but the -1 over 4 part is right.
Yeah, it goes to 0. Never mind.
Right, and isn't x to the 0 just 1, so you got a number.
Yeah.
Right, now, we do the inside, don't you get the same guy? And then if you go for the last, well, again, got to be careful, -1/2 x to -1 times itself. Well, two negatives make it positive. A 1/2 and a 1/2 get you 1/4. And when you combine the two powers, you get x to -2. Are we happy with 1/4 x to -2? Okay, now you tidy everything up. And that 1 and that -1/2 ends up being plus a 1/2 in the middle. And you get that. Hey, we have 3 guys that are going to be inside the square root. 3 guys inside the square root better be a perfect square. So let's find the perfect square. What will the 1/4 x squared get me?
1/2 x.
And what will this guy get me?
1/2 x to -1.
Now, I want to show you something that happens so many times. It's not quite a rule, but it's a cool thing if it works. Do you notice that this derivative here and this guy here are almost identical? Do you notice that's a negative and this is a positive? You see that? The derivative is these 2 terms, and this guy squared is the same 2 terms but with a plus. You remember this guy, the derivative? Right, the one we just did? Hey, same 2 guys, but a plus. Did you see that? Those 2 guys with a negative. Same 2 guys with a plus. That's not just a random coincidence. Now, it doesn't happen all the time, but it does happen a big majority of the time. And it's normally a good signpost that you're doing it right. So the arc length then is the integral from 1 to 4, the square root of this guy. That becomes the integral from 1 to 4 of 1/2 x last question, because it's going to be dot, dot, dot after this. That should have been a 1/2 x plus a 1/2 x to -1, right? That's what I should have written down. I changed the 1/2 x to the -1 to a 1/2 1/x. Why did I do that? It wasn't just cosmetic.
Natural log.
Yeah. If I write it like this, won't I see the answer as a 1/2 natural log x? If I left it this way, couldn't you try and do the power rule and get really annoyed because it doesn't work? Right? Oh, it's a power. Add one a power, divide by new power. Wait a minute, the new power is 0. What's up? Well, what's up is that it's not really a power rule. It's a log. Right, now that's essentially the same question as I did earlier, but it had about half the lines in it, right? Do you get the flow of these questions? How they kind of go the same sort of a way each time. They may start off looking a little bit different, but they end up being the same. They end up being a perfect square, at least in these two. Let's find another guy that is a different kind of perfect square. I saw one earlier and I thought, oh, that's a cool one. Can never find one when you want it. Where is it?
Professor,
Yes.
with that derivative for the 1/x term, would it be 1/2 natural log of x?
Yes.
Okay, thanks.
That's why I kind of separated out the 1/2. If you left it as 1/2x, you really technically have to do a u sub of 2x on it, which is a extra work. You get the answer, but you have to make sure that you do a u sub if you leave it as 1/2x. So it's easy to call it a 1/2 1/x. That's why I chose that. I know it's in here somewhere. It's a log of a secant or a log of a cos or something, if I remember it right. Which of course I don't. Where the heck are you hiding? I want to do one more of these weird guys. Where are you hiding? There it is. This is a version of question 7. And the function is the natural log of secant x. And evidently you're going to do it from 0 to pi upon 6. This one's not quite the usual perfect square. This is a trig version. Okay, I need to differentiate the log of secant x. Would you agree that's a chain rule? Right, we're in differentiation world, it's a chain rule. If you differentiate a log, you get 1 over the thing, followed by the derivative of secant x. Okay, this will sort you out. Get the old cobwebs moving here. What's the derivative of secant x?
10 squared.
Nope, that's the integral, and it's secant squared gets you tan.
Secant 10.
Yeah. We do integration, but half the time we end up differentiating, don't we? And sometimes your brain is going uphill when it should be coming downhill, right? You're integrating something using an integration rule when it's really a differentiation situation. Now, in this case here, they cancel out and you're left with tan. Now, if you 1 plus this guy, you get 1 plus tan squared. Now, this is a perfect square, not in the usual, 3 terms quadratic ones, but this is still a perfect square. What is 1 plus tan squared x equal to?
Secant squared.
See the little blighter? Right, the little sneaky? Trig does that, doesn't it? Trig has its own world, its own rules. You've got to figure out identities, which means that we can now get the arc length. It's going to be the integral from 0 to pi upon 6, the square root of secant squared dx, which is the integral from 0 to pi upon 6 of secant x dx. Does anybody... Oh, this is asking too much, but it could happen. Do you know I wrote that down about, darn it, Friday, I think.
Isn't it like the natural log of secant of x tangent of x or something like that?
Not only is it something like that, it is exactly that, Matthew. You get the
Oh.
prize today.
Yay.
Now, what would you do? Wouldn't you go and look at the table of values and find it? You should be able to look at that and say, that isn't one that I'm meant to know, right? If it was said the integral of sine x, I'd say, yeah, I know what that is, right? But in this case, then, you then evaluate it, and you still have some sneaky stuff. Don't you have to find the exact values of secants and tans of angles like pi over 6? But at least you're well on the way to finishing, right? So just to show you a different version of a perfect square. So to me, a perfect square is anything that ends up being inside the square root is a square, right? A single square. Are we good? Right. Should check the time. Oh, going faster than I thought. I want to do a fractional power one, so you're going to hang in here while I figure out what the heck a fractional power one looks like. Well, that one could work, I guess. We'll do 11. Okay, a couple of things. Firstly, that guy's not written the way it needs to be. Doesn't it have to be written as y equals a function of x or x equals a function of y? Agreed? Not x squared equals something, but just x. So let's take care of that. If x squared is this, what will x be? What power goes here?
X to the 3 halves.
Correct. Now I'm going to put the arc length thing in. These two darn guys are the start and finish. Isn't this going to be the square root of 1 plus, I'll call it g dashed of y squared? Basically, that guy is g dashed of y, right? dy. Now, what's important is that in this version, isn't it y that's a variable? So shouldn't the boundaries, the limits of integration, be the y values? Now, what you normally get is from 1 to 2, right? They tell you it's not an issue. Can you see that the y values come from this to this? So that's why this is 9 and this is 17. Are we comfortable with how I found the limits of integration when they just told me the coordinates of the start point and the coordinates of the finish? But at that start point isn't the y9, and at this finishing point isn't the y17. So that's them. Are we cool with that? Okay. Pause with that fella. Return to this guy. If you want to write it this way, me personally, I don't know what it is. It's probably just psychological. It just is easier in my brain if I call the x g of y. Because when I see x's, I sometimes get thrown, right? I'm not used to x's being the variable that I sometimes forget that in this case, the y is the variable, right? So we're okay with that little tweak. You don't need it, but for me, it helps. Let's differentiate. Well, multiply by the power and reduce the power by 1. 1 plus the derivative squared. 1 plus so the algebra could catch it out here. 3 over 2 y minus 8 to a half, right? Being squared. Now, isn't there a rule that you can square the individual pieces? Right, so the top number gets you 9. The denominator gets you 4. What does y minus 8 to the power of half when you square it become?
Y minus 8.
Okay. Now, if I multiply this through, I get this guy, take away 18, and then I end up with that guy. Have you noticed it's not a perfect square? Because I'm now showing you an example where the square root ends up just being a linear term. So our arc length is the square root from 9 to 17, the square root of this. Okay, where do we go next? There are two correct methods. Either one will do for me. You got you stumped? What you gonna do? Square root of a linear term. Okay, last chance.
Do you
Do I
just
use-
do the square root? Oh.
Oh, well, you might be telling me version 2. Can you do a U-sub? Can you trust me a U-sub eventually works? Right. Now, you were about to say something to do with a square root. Do you want to repeat it? We'll see if it's what I hope it is.
You just do it? You just do the square root?
Not quite sure what that means. If I write the square root as a half power, can't we do the linear shortcut method? Add 1 to the power, divide by the new power, and then what happens to that 9/4? How do you cope with that? You then go times 4/9. I'm not sure if that's what you meant. You're not allowed to take the square root of both individually. If that's what you meant, that's not allowed. But that would be the other way. I'd probably do a U-sub because the numbers are so weird and ugly that you might get thrown off. Okay, dot that, then you can finish it off. 5 minutes later. Anything about that question that is puzzling, or you think you got the flow? Going to move it. Okay. Now, I guess I should do one more before I do arc length functions. Has anybody been doing these questions or get stumped on something that you might want me to do? I'm just scanning through it. Most of them are perfect square questions, and I think I've done quite a lot of perfect square questions. Let's see if there's something at the end we can do. Oh yeah, we can do this. There's a number of questions starting at, is it 15? Yeah. So from questions 15, 16, 17, 15, 16, and 17. Do not evaluate, they say. All they ask you to do is to set them up. So you're not even going to plug it into your calculator, you're just going to set up the integral. So let's pick one of them and see what happens. This is 16. The function that we're going to set up is this fella. We don't actually get the answer, right? We don't take it to the end. We don't even need to do things like make it a perfect square or even plug into your calculator. We kind of finish when it looks like this, right? When it's all done. So if you do the derivative, how are you going to differentiate x e the power of x to the 6th? Ooh, that's messy. How do you differentiate something that looks like this? What rule?
Chain rule.
Well, there is a chain rule involved in this guy, but there's something going to happen before that chain rule.
Oh, is it the product rule?
Yeah. Because it's technically it's two things multiplied. So it's going to be f dash g plus f of g dashed. Differentiate that, you get 1. Leave that guy alone. Leave that guy alone. And now the chain rule. The chain rule happens when you differentiate this ugly guy. Okay, now according to the chain rule, don't you get e to the power of that guy times the derivative of that guy, which is him. So that is that guy, this guy. So far, so good. Algebraically, is there anything I can do to this to make it look a little bit prettier? Any ideas?
Factor out e to the x to the 6.
Yeah. It's not a lot, but you do what you can, right? Okay, let's square it and add 1. Well, that's going to be 1 plus. I don't want to have to write all this in a bracket with a square, so let's cut out a line of working. This is going to get squared. Now, when you square something, don't you square each individual piece? So this piece here just gets squared. What happens to this ugly thing if you multiply it by itself?
Would it be e to the 2x to the 6?
Yeah, not x to the 12, but 2x to the 6, correct. And so we are ready. It's going to be the integral from 0 to 5, the square root of that. And you stop there.
Could you just
There we
scroll
go.
up just a little bit? Thank you.
Are we good on that? A little different? I think I'll keep the arc length function till tomorrow. That gives me time to play about with a really ugly one that I haven't done yet. Okay. It's over here somewhere. Okay, let's where the heck are you? It has an inverse sign in it. I want to do an inverse. There we go. This is like number 9. Last question for today. Oh, while I'm setting this up, say hi so you can get attendance. Why does that not look right? You're seeing the screen. Does this screen feel like it's sloping from left to right, or is it my one eye issue? Does it look horizontal to you?
Looks low cricket, but not bad.
Not bad. No. Yeah, one of the things, if you've only got one good eye, is that, see when you try and do things horizontal, I tend to be like 5 degrees out. So when it looks horizontal to me, it's like 5 degrees out. And so I guess when it is horizontal, it feels wrong to me, if it's noticeable. But if that's fine, it's fine. Okay, I know I'm going to have to differentiate this guy, and God in Himmel, what an ugly function. That's why it's the last one. This fella has to be rewritten to allow differentiation to take place. What do you think I'm going to change the square root into?
2 to the power of 1/2.
You agree? Now, the inverse sign is totally okay. But shouldn't I call the square root of x to the half? So really all I'm doing here is setting up the original function in a format that is going to make differentiation easier. In other words, fractional powers, right? Now I'm going to give you a warning right off the bat. This is going to get ugly really quickly. You can kind of see it's going to get ugly really quickly, agreed? Yet at the end, it's going to be remarkably nice. Doesn't look like that has any chance of happening, but trust me, it's going to get really nice eventually. Okay, let's do the derivative. This is a chain rule, right? So it's multiplied by the power, reduce the power by 1, and then you finish by differentiating what's in the bracket. So 1 take away 2x. I'll be happy with the derivative of that is all of this. Comfortable with that? Okay, this one will get the cobwebs out. And don't worry about the x to the half or whatever. What is the derivative of an inverse sine?
1 over square root of 1 minus x squared.
And instead of x squared, I'm just going to call it something squared, right? So in this case, since this is x to the half, don't you get 1 over the square root of 1 take away this guy squared, which is x. Are you happy where that came from? 1 over the square root of 1 take away something squared. And x to the half squared is x. And before I forget, it's a chain rule. Right? If it ain't x, it's a chain rule. So shouldn't you finish with the derivative of x to the half? Which in itself is a little bit messy. Would you agree that this is not looking good?
Yes.
Isn't it
For-
negative 1/2 x to the negative 1/2?
Well, it's multiplied by the power force, then reduced, so it is still positive. If you differentiate x to the half, you get 1/2 x to the negative a half. Differentiation power, take away 1 later.
Oh, okay. Thank you.
Right. Now, I am going to do style points on this. Style points is factor the heck out of it and make it look like the original. Great? That's the usual rules. And this is going to take a couple of lines, but it's going to, I hope, explain to you why I push style points so much. If I left it the way it is right now and tried to square it, can you trust me that you would have a headache? Because it would just not end well. Agreed? So I'm not even going to go near squaring this. That's a mistake you might make. I'm going to do style points on it. 1 minus 2x, that's this guy. 2 on the bottom, and this guy on the bottom. This fella here is 2, x to the half on the bottom, square root of 1 minus x. Are you happy about the movements that I've done right now? Is there any one of these that you're not sure about? If it feels good, I'm moving on. Okay, I'm taking that as a good sign. Now, according to style points, you factor the heck out of it, and you make it look like the original. It's nicer, but not perfect. Uh-oh. Can you see what I did to get this fella to become that fella? You notice that square root times square root? Can't you bring them inside and go x and x? You see that? Now, why is that such a good idea? Will you have a look at your two ugly fractions right now? Aren't they the same? And if you share a common denominator, then you should be able to add them together as a single fraction. And that means then I should be able to do this. Looking good. Not so obvious what I'm going to do next. Is there anything I could do to the top line that might be kind of helpful?
Factor it, then get rid of the 2's.
Oops, one of them's wrong. You got to hang in here. This is just the derivative, as nice as I can get it. There's actually a little tweak I could do, but it's not necessary, so I'm not going to. But has anybody got a guess of what tweak I could do if I really was trying to, do some more?
Factor x in the radical.
Right? And then it would partially cancel with that, and I'd end up with the square root of 1 minus x over the square root of x. Right? And it would work fine. But this version is going to work, so I don't want to do too many weird things because there's already enough weird stuff going on. But you're right, that's what I would have done. So all I know right now is that this is what that guy looks like. So let's square him. Well, won't you get 1 minus x squared over x take away x squared? You happy about top square, bottom square? Are we good with that? Now, if I pull out an x from the bottom, we now get that. Which means that it becomes that. Which can be separated into that. And now I'll do a 1 plus derivative squared. And God, would you look at it? 1 over x. So the arc length is the integral, well, they don't tell you, but it's from 0 to 1 of the square root of 1 over x dx, which is integral from 0 to 1. Is it 0? Well, who cares about this? Dot, 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 right? Compared to what that is, would you have thought that the final square root would have just been a square root of 1 over x? Which, by the way, is 1 over square root of x, which is x to the negative a half, right? Look at that. Come on, that is kind of cool, right? Okay, maybe it's one of those tastes that you develop in the future, right? Maybe it is, but I think it's cool. Just the pure joy of how something so ugly ends up being so pretty. I mean, I think it. Yeah, I know. Anyway, that is us for today. I shall see you tomorrow, where we will look at what's called arc length function and start improper integrals, which is 7-8.
I still haven't gotten the email for the test grade.
I thought I'd sent it to you, Jason. Have you checked lately? I sent it to
Yeah.
you about an hour ago. No? We're having issues with me sending emails to you because I'm receiving that email because I did. I remember
I
it.
also haven't gotten one.
I haven't gotten one.
Me neither.
Oh,
I didn't see
good.
one in my student email.
Right, now 2 questions here. I sent out a batch email with your grades. So basically you're saying none of you have seen this.
Yes.
Okay. It said it left. I saw the little names disappearing in my mail merge. But what it says and what it does are not the same thing, right? Try again. I'm not sure. It happened before. You've received your grades from me before. And I do the same thing. It's not like I do a different thing each time. And the fact none of you are getting it sounds like it's on my side, not your side. Okay,
So
I
you
will.
said it's sending to the WebAssign email?
It's not sending, it's sending it to your student's email or whatever email you used in WebAssign. So in WebAssign, some of you use your Olympic student email and some of you use Fred at yahoo.com. So it's using that email, the one that you registered WebAssign with. That's what it was sent to. So you want to go looking at that in case it's there, because that would be nice. Maybe
I checked both, but maybe I need to change it to my student email.
Well, that would be good for other reasons, yes, but not anybody. Has anybody in this class got that? Nobody got it, so it's my fault. Somehow I'm not doing it right. Okay, bye-bye, guys. I know your time is busy and I've kept you probably longer than I should have. I'll hang about for 5 minutes if you have any questions. As soon as this is finished, I'll go back and try yet again to send out that email with your grades on it.
Thank you.
Right. I don't want to send 25 separate emails. That would take me forever and a day. So I'm trying my darndest to use mail merge. Right. I'm assuming some of you are here because you have questions, right?
I got a small one.
Go for it, Ian.
It's going to be on the first lesson. It's going to be integral of square root of 49x squared plus 16, all that over x squared. And I feel like I have to get rid of the 49.
You do.
Yeah, but I don't.
So how to, right?
Yeah.
Okay, let's show you how you do that. You have to do a U sub. And the U sub you're going to do is 7x. Okay, so du by dx is going to be 7. So eventually 1/7 du gets you dx. So far so good, right? Now 49x squared is basically just u squared. So now what you have is u squared plus 16. The du is a 7th, goes there. And x squared is a bit messy. But if u equals 7x, then 1/7 u is x. So x squared is 1/49 u squared. So you get 1/49 u squared. Now that goes in the bottom, that goes in the top, they partially cancel. And what you now have is that guy. Now, are we talking table of values or are we talking x sub?
Table of values.
Right, so pull out that 7 and go hunting for him. If it had been an X sub, you would have called it a U sub, and it would have been 4 tan theta. If it's table of values, then that's where you go.
Okay, thank you.
You're all welcome. Okay. Who's got the next question? Just first come, first serve.
I'm having a hard time plugging in the equation into my calculator when it's when the equation's equal to x for number 2.
Number 2.
Yeah.
So, okay, so you're going to have some weird integral, which technically has got y's in it. Is that right?
Yep.
I'm looking at this fella here. It might not be this particular guy, but it will look something like this. Right? Is that the kind of look to it?
Yeah.
Okay, let me see if I can try my calculator guy. Oh, he's missing. Okay. I used to have an emulator. It's kind of disappeared for some reason. Okay, I'll show you the calculator. Physically, that'll do it. All right. So, basically, there we go. We are going to try and figure out how to type that into our calculator. So let's clear this out of the way. Go Y, clear this out of the way. Basically, call that X, and you're fine. So it's going to be a square root. Check. Then a bracket, which means gives 1 plus the start of another bracket, 1 divided by. That's not good. If I type in 2 square root of x, you might think I'm doing 2 square root of x, but there's a very good chance the calculator thinks I want half over something else. So just to be safe, I'll put another bracket and go 2 times the square root of x. So that's that bit. Subtract 8, close the brackets, squared, close the brackets. So that's what 1 plus 1 over 2 root y, take away 8 squared looks like. And those brackets are pretty important, and the number I've got and the way they're pointing are also important. Right. In this question, I think it's going from 1 to 4. Okay, from 1 to 4. Let's figure out what to do next. I go to Zoom. No, I don't. I go to Window first, and I say start at 1 and finish at 4. Sometimes if you just use a general window, there's a vertical asymptote and the calculator gets really annoyed at you. And now I'll do zoom to fit, which is zoom 0. And I kind of do that to make sure that everything looks good. And what you want is a pretty boring curve, which is good. And now I want to find this integral, which is essentially the area under this weird curve. So you go second calc, option 7, and it says lower limit, so you press 1, enter. It says upper limit, you press 4, enter, and then you wait for that little fill-in thing because it likes doing that. And 23.1948, and that is the answer that I have on my screen beside me. Have we got it?
Thank you.
Okay. Who's next? Are you just watching, James, or do you have a question?
I no longer have a question.
Okay, what you got for us, Douglas? Do you have a question? I've got 3 people. If none of you have got a question, I guess it's the end of the day.
All right, thank you.
Okay then.
I had
Bye-bye.
one, but I just didn't
Okay.
want to. It was about from the
You
test.
wanted to, is there a question? James, I think, wants to ask something that just me and him need to talk about. So if the others are finished with their questions, they can leave, please.
Thanks.
Noah, if you're here, or if you can hear me, could you leave now, please? I guess he's left it on. Okay, what you got, James?
It was just trying to figure out how to. It was question 7 in the test, and I hadn't really figured out how to solve it.
Okay, do you have a copy of the question on top of your head? Or at least something like it?
Yeah. It was just the interval from 0 to a of 9x squared to the square root of a squared take away x squared. I think I said it. I said it wrong. Yeah, that's it. Sorry.
No, I think I got it. Right. That's the guy?
Yeah.
Okay, so we need to know what kind of X sub it is, right?
Yeah.
That's the start. Okay, if that was 25 or 16, it wouldn't be a problem. So I'm assuming that you don't really have a problem with the a squared minus x squared.
No.
What would this correct? Maybe that is your problem then. What is the X sub that you would use in this story?
It would be x, a sine of theta.
Okay. So I guess I have to go through the whole stuff because I don't know where you went wrong. Or is there a bit you're stuck at?
I think where the trouble for me came is when it comes to, this all turns down to sine squared, cosine squared.
Okay. So how do you deal with sine squared? I guess it's theta, right? Cos squared theta, right? D theta.
Yeah.
Okay. There are two different approaches to this. Both work. I'll take what I think would be the simplest one. I know that the sine of 2 theta is 2 sine theta cosine theta.
Mm-hmm.
Another way of thinking about that is that a half of a sine of 2 theta is a single sine theta cosine theta. And if I square this, then that guy is the same thing as a sine squared cos squared theta, right?
Yeah.
So what I've done is I've changed a double square into a single square. And then I use a different formula. You remember the guy that says sine squared x is 1/2 1 minus the cosine of 2x? That guy?
Yeah.
I'm going to use it, but think of x as a placeholder. So it's sine squared of what you give me is 1/2 1 minus cosine of twice what you gave me. So this is going to be 1/4 of 1/2 1 take away the cosine of 4 theta, which is 1/8 take away 1/8 the cosine of 4 theta. So this becomes 1/8. Actually, let's stick it out there. 1/8 of 1 take away the cosine of 4 theta. Looking good?
Yeah.
Now, integrate, you get theta. A cosine gets you a positive sign, so that's negative that fella. Of course, you're going to have a quarter. You're going to have an 1/8. So you get to here. Now you have to get your triangle, and you have to turn these guys into something that you can plug an a into, I guess. So if x is a sine theta, then x over a is sine theta, and that we like, because that gives me opposite adjacent hypotenuse. That gives me an x over a, which gives me exactly what we'd expect. That guy, right?
Mm-hmm.
Of course, theta is easy. Theta is just going to be the inverse sine of x over a. That's not easy. Because if I want to, I'll forget about the quarter right now, and if I just focus on doing this guy, this is only good for sines and cosines and so on of theta, not of 4 theta. So I have to recognize that that's 2 times the tan of 2 theta, the cosine of 2 theta. It's a little bit better. Of course, is it the sine of 2 theta, 2 times the sine of theta, cosine theta? And isn't cos 2 theta, cos squared theta, take away sine squared theta. If you go through this triangle, then can't you replace all of these various pieces using this triangle? And that will tell you what this cell is equal to in terms of x. And it's downright ugly, but doable, right? Do I need to go further, or do you,
The
can
only
you
thing
see what
is,
to do?
can can you find out a cosine squared from that triangle?
Yeah, just find a cosine and then square it. Oh, as an example, right? Cosine of theta is the square root of that guy, right, over a. So cos squared theta will be that guy. Just
Okay,
square the top.
that makes sense. Okay.
Right. And you'll find the sine squared and the cos squared share a common denominator, and they cancel out really nice. And if you multiply these two guys together, you find out there's a little bit uglier but doable. And then after that, you just plug in 0 and a, and 0 is good because that takes care of a whole load of the ugliness. And a matches quite well because it makes other things disappear as 0 as well. So the final answer isn't as ugly as you might expect it to be.
Yeah. Oh, that makes sense. I did algebra a long time ago.
Yeah, well, you're not the only one. Oh, Noah, you like that? Okay, Noah was here.
Yeah, I had a question about that kind of, so I stuck around.
Okay. Do you mind if I keep this as well on the lecture?
No, that's fine.
Are you sure? Okay. Then if that is us, I'm going to go and try and figure out why I can't send you your grades. Or what I'm doing wrong that I wasn't doing the last time I did it. I can't think of what it is, but who knows? Are we good? Right. Bye-bye, guys.